Okay, guys, here is a solution to a pretty recent question from the 2015 Physics 1 free response question. So this was the first year of the Physics 1 exam. And here we have kind of a similar setup, except for this time, although the frequency, it's going to be resonating. It says that it's fundamental frequency, so F1, but with 4 different strings. So each one of these are a different string here. Okay, A, B, C, and D. And so we can see that they all have different fundamental frequencies. So something is obviously different about them. But very importantly, the length of them is the same, and the mass of the block is the same. It tells us to ignore the friction in the pulley. Okay, so this oscillator, the frequency will change in order to get this to mode 1, essentially, the fundamental frequency. So the mode number is going to be 1 for all of these. Okay, so let's take a look. And right below here, it does give us the information that the velocity of a wave on a string is equal to, and so I'm going to use how they wrote it here, tension over m over L, which little lowercase m here is the mass of the string. Okay, we have been using this as, I'll write it how I'm familiar with it, is tension over mu. Alright, so this right here is mu. I'll use a different color. So this is the linear mass density. Okay, so if you were worried about memorizing that equation, as of 3 years ago, this question was given to you. Okay, so let's start with part A. What is different about the 4 strings shown above that would result in them having different fundamental frequencies? Explain how you arrived at that answer. Okay, so let's write down information that we know. So capital M, the mass of the block is the same. So the tension is constant here. Also, we know the length of the string is the same as well. Okay, so if we're looking at this equation, this is constant, and this is constant. So there's only one thing that can be changing, and that is the mass of the string itself. Okay, because from our wave equation formula, okay, all of these are going to have the same wavelength because they're all going to be mode 1. Right? So this is 2L over 1, so just 2L. So all of that's going to be constant. Now this does change, okay, but why is it changing? So we want to look at this end of the equation, and it's because of the mass of the string. That's the only thing that can be influencing this. So we want to essentially reinforce this. So we've kind of explained it verbally, but maybe we want to give a mathematic explanation as well. If you have the time, it cannot hurt. Okay, so from here, and I'm going to start it out like that. Okay. Okay, so the frequencies do change, but lambda is constant. Okay. We know that is also a constant. Alright, so to quickly simplify math, because oftentimes in physics we just care about proportionalities. Okay, so that's kind of what we're left with here, is that the fundamental frequency is going to be proportional to 1 over the inverse of mu. Okay, and we can expand that even more. So since mu is m over L, that would be L over the square root of, and that's the mass of the string, just remember. Okay, so this is as simplified as we can get. So the fundamental frequency is going to be directly proportional to 1 over the square root of the mass of the string. Okay. All right, I think that solves part A pretty well. Part B, a student graphs a frequency as a function of the inverse of the linear mass density. Will the graph appear linear? So what the graphing is f1 versus 1 over the inverse of the linear mass density. So that's 1 over mu. Okay, which is, going to look L over M. And remember that as constant. So essentially, what the graph is, it's basically this. 1 over the mass. Okay. So this says, is this a linear relationship? Is this going to be a linear graph? Well, on the previous page, we saw that the relationship between these variables is this. So it doesn't ask us what type of graph it would be. It just says, is it going to be linear? And from what we drove in part A, this is clearly not a linear relationship. So graphing this will not get us a linear relationship. Okay, part C. I will try to maybe recreate this. Hold on. Okay, so here's part C. It says the frequency of the oscillator connected to string D, which had a fundamental frequency of 350 hertz, changed so that now the string vibrates in its second harmonic. Okay. On the side view of the string below, mark and label the points on the string that have the greatest average vertical speed. Basically, label the middle of the antinodes. Okay, now keep in mind, guys, that all of these questions from 2015, 2016, 2017 are all available online to find on the AP website. If you need a better look at this question, because this is going to be where highest vertical speed is. right? Because that's where they're going up and down. So second harmonic, that means we're just going to have two antinodes. And this black line here is me trying to indicate kind of like a center line for the string to make it easier for me to draw. Okay, so let's let's make that a bit bigger. Alright, what I'm going to do is I'm going to kind of label our nodes, because I know it's going to have 3 nodes for mode 2. Okay, so this is going to be like this, and I will draw the underside a different color. Maybe this blue. Okay, so that's like the returning wave. Okay, so all you need to do is label where the points of highest vertical motion are. Okay, and that would be here and here. Right, so both points. Right, that's the center of the antinode, and that's really it. It's a pretty easy wave equation, wave question.